Lunch semua. Have you had your lunch?
Dah.
Dah.
Okay. Okay, now nampak skrin kan?
Nampak.
Okay. DC voltmeter. What is DC voltmeter? So same with previous lesson, we from PMMC construction or from the unsolver meter movement, we design ammeter. Okay, so now we want to design voltmeter from the PMMC construction. Later on, we will learn about ohmmeter. Okay, how to design ohmmeter, DC ohmmeter from PMMC meter movement. Okay. The unsolver instrument can be constructed as DC voltmeter by connecting a multiplier RS or series resistor with meter movement. In ammeter construction, we put R shunt. Okay, we put shunt resistor parallel to RM. In DC voltmeter, we put additional R, or we call it as RS, or series resistor or multiplier resistor series with the R-solver movement or with meter movement or PMMC. As DC voltmeter measure the potential difference between 2 points in a DC circuit. Okay, what's the function of RS here? To limit the current through the meter as to not exceed the full scale deflection of current. So this is a typical function or typical role of resistor to limit the flow of current. RS value, to find the value of the multiplier resistor, okay, it is required to determine the sensitivity of the meter movement. S is equal to 1 over current, IFSD. So in DC voltmeter, it is series connection. So the current, only one current flows through this connection or through this path. Okay, so you do not mind about which current, okay, because only one current flows through this path. S is equal to 1 over current. The unit is ohm per volt. Okay, we know that I is equal to V over R. Okay, so if 1 over R, so R over V. So that's why the unit for sensitivity is ohm per volt. This is the definition for DC voltmeter circuit. As usual, we know that IM. Now IM is equal to IFSD. It is the current flows through the meter, but the same current flows through the RS, to the whole circuit. RM is internal resistance of the movement. RS is multiplier resistance or series resistance. V is full range of the voltmeter. Okay. The unit of sensitivity express the value of the multiplier resistance for the 1 volt range. To calculate the value of the multiplier for voltage ranges greater than 1 volt, simply multiply the sensitivity by the range and subtract the internal resistance of the meter movement. So our total in this circuit, our total is equal to, so we have RS and RM. RM is the internal resistance of the unsolver movement. RS plus RM. Okay, so our total is also equal to S multiplied with voltage range of the voltmeter. This is the formula. Our total is equal to sensitivity multiplied with the voltage range of the voltmeter. Okay, so if you want to get RS is equal to R total minus RM or RS is equal to S multiplied with V range minus RM. Okay. And also we know that S is equal to R total divided with V range. Any question up to here?
No, Doctor. Yeah.
No. Okay. Okay, this is the example. Calculate the sensitivity of a 200 microamp meter movement which is to be used as a DC voltmeter. So we have current here. So which current? Don't worry because this is series circuit, only one current flows. Okay. So calculate the sensitivity. S is equal to 1 over current. 1 over IFSD is equal to 1 over 200 micro. So this is the sensitivity of this voltmeter, 5 kilo ohm per volt. The unit is ohm per volt. The sensitivity is based on the fact that the full scale current of 200 microamps results whenever 5 k ohm of resistance is present in the meter circuit for each voltage applied. Okay, so 200 microamp is not the range of the meter because this is DC voltmeter. Okay, this is the current that flows through the meter or to the MMC. Okay, the next example, calculate the value of the multiplier resistance on the 0 to 50 volt range of a DC voltmeter that uses a 500 microammeter movement with internal resistance of 1 k ohm. So the question is to find RS. Okay, how to find RS? Okay, this is the formula. RS is equal to, this is R total, or S multiplied with V range minus RM. Since we do not know what is the R total, but we know that R total is equal to S multiplied with V range. So we have to find the S. S is equal to 1 over current, 1 over 5 microamp. It is equal to 2 k ohm per volt. So RS is equal to, we substitute S is equal to 2K here, multiply with the voltage range of the voltmeter 50, and then minus RM is given 1K, we get RS is equal to 99 kilo ohm. Okay, this how to find RS from this equation. V is equal to IM in the bracket RS plus RM. This is Ohm's law. So if we take out RS here, it is equal to this, and finally we get this. But I think do not need to memorize this. We just use Ohm's law. Okay, no need to memorize. Okay, a basically observable movement with a full scale deflection of 50 microamp. This is the current flows through this voltmeter, and internal resistance of 500 ohm, meaning that this is RM. Okay, internal resistance is used as a DC voltmeter. So this statement, a basic observable until 500 ohm, is the statement for PMMC. Okay, so this PMMC is used to design a DC voltmeter. Okay, PMMC is built-in DC voltmeter. PMMC will create DC voltmeter with the addition of RS. Determine the value of the multiplier resistance or RS needed to measure a voltage range of 10 volts. So if we use the previous formula RS, the question is to find RS. RS is equal to this as previous formula. If we use this formula, we get the answer. But I don't like to memorize the formula, so we derive from the basic formula. S is equal to 1 over current. 1 over 50 microamp equal to this, 20 K. And then RS, we know that RS is equal to R total minus RM. R total is equal to S multiplied with V range. So we substitute S equal to 20K here, multiply with the V range, 10 volts. Okay, minus RM, RM is given 500 ohm. We get this. Okay, same as from the formula. Any question? Can I understand?
Can.
Okay. The next question. The next question is to calculate the value of full scale diffusion current and multiplier resistance. So you have to find current and RS on the 50 volt range. The V range is given of a DC voltmeter that has a sensitivity of 5K ohm per volt with an internal resistance of 100 ohm. So the PMMC has 100 ohm RM. Okay. This PMMC create voltmeter with 50 V range with sensitivity of 5K ohm per volt. So you have to find the IM or IFSD and RS. So find it yourself. You can compare your answer with your friend, okay? Multi-range. Okay, I think we go to tutorial first regarding basic voltmeter. Orang dah ni. 39. Okay. This is tutorial 2 solution. But I did not upload in Microsoft Teams yet. Okay, DC voltmeter. Number 6. So last time on Monday we did until here, right? Okay, so number 5 is on voltmeter. A PMC instrument. Okay, this is PMC instrument with a FSD of 100 microamp. Okay, 100 microamp flows through the circuit and a core resistance of 1K. This is RM. In figure 4, this is figure 4. It's to be converted into a voltmeter. So PMMC with this characteristic 100 microamp and RM1K will be converted into a voltmeter. Okay, determine the required multiplier resistance or R, no R shown here, but RS. If the voltmeter is to measure 100 volt at full scale. Okay, so the voltmeter range is 100 volt. So you have to find RS. Also calculate the applied voltage when the instrument indicate this. Okay, so we want to find RS. RS is equal to S multiplied with the V range minus RM. Okay. And S is equal to 1 over current, 1 over 100 micro, we get 10K ohm per volt. RS is equal to, we substitute S is equal to 10K in this, multiply with the voltage range is 100 volts, minus RM, RM is 1K. And we get RS is equal to 999K ohm, meaning that RS here is 999K ohm. RM here is 1K. Okay, so the next is calculate the applied voltage when the instrument indicate 0.75, 0.5, and 0.25 full scale deflection. Meaning that when the needle of the meter, imagine that this is analog meter. When the needle of the meter indicate 0.75 of the full scale of the screen. What is the voltage? What is the voltage? What is the measured voltage or the applied voltage? How about when the needle indicate at half 0.5, half of the scale or half of the screen, and how about at 0.25? So we know that the full scale range of the meter is 100 volts. So if 0.75, meaning that 0.75 multiplied with 100, 75. Same goes for 0.5, we get 50. 0.25, we get 25 volt. Okay, how about the voltage range is 50 volts. Okay, what did you get? 0.75 of the full scale. Let's say the voltage range is 50. So, what's the answer?
37.5.
Good, 37.5. Okay, how about 0.5 full scale deflection? Duhai. Duhai? Are you with me? Duhai, are you with me? Duhai, are you with me? If you cannot answer, I assume that you are absent. Say something or write something. Duhai? Duhai, are you with me? Sometimes students exist in the class, but they sleep beside the laptop or they go somewhere, right? Just log into the class. Duhai, are you with me? No answer. No response. Azim. What's the answer, Azim?
Ya doktor.
Jawablah. Saya tanya apa tadi?
0.35 daripada apa tu? Doktor punya soalan.
Apa? Tadi buat apa?
Saya lupa buat.
Lupa apa?
Lupa bawa kalkulator doktor. Saya kat library.
0.75 from the full scale of voltage range. The voltage range is 50.
Oh, 50.
Congak. Macam mana?
0.75 daripada 50 kan? 0.35? 0.45. Betul. 0.35 ke?
Mana? Your friend answer just now. 37.5. Lain kali buat kalkulator.
Okay.
Okay. How about 0.5 full scale deflection? Let's say the full range is 200 voltage, 200 volt. Lukman. Akmal Lukman.
Yes, madam. 0.5 from 200, right?
From 200.
Yes, 100 volt.
100 lah, tak congak Okay. So, when the V range is 100 volt and the needle point at 0.75, meaning that here. Okay, this is the full range, 100 volt. So consider that this is analog meter. So DC 75. So this is how we design. You imagine that we want to design a voltmeter. Okay, and then we want to make the full range to be 100 volts. And we have calculated all RS and what else? RS, okay? We have to design RS, the value of RS. So we found the RS. We found the RS. And then we want to mark, okay, what the value at the 0.5, at 0.75 of the full scale, at 0.25, or at 0.1 here, meaning that at 0.75 full scale depression is 75% of the full scale, full range. Understand or not? Can you understand?
Yes,
Can.
yes, Doctor. Can.
Can. Okay, ni apa? We go to multi-range voltmeter. A DC voltmeter can be converted into a multi-range voltmeter, same as the ammeter, by connecting a number of resistors in series with the meter movement. So this is resistor connected in series. Or we can range like this. R1, R2, R3, R4. All the R connected in series. Okay. What's the difference between figure A and figure B? What's the difference? What's the difference? The difference is R1, R2, R3. R1, R2, R3 is RS. Okay, RS1, RS2, RS3. RS1, RS2, RS3. Okay. The arrangement in figure A, the RS is arranged like in parallel. In figure B, the RS are connected in series. Okay, but all the are connected in series with the PMMC. All are in figure B connected in series with PMMC. With the meter movement using multi-position switch. All multiplier resistances except the lowest range R4 have the standard value and also very precise intolerances. R4 is the only special resistor which has to be specially manufactured to meet the circuit's requirement. So if we refer to figure B, the closest resistor to the PMMC is the lowest range of resistance as compared to other R. Okay, this is an example. Convert a basic unsolver movement. Okay, this with an internal resistance of 50 ohm. Okay, this PMMC has RM of 50 ohm and a full scale deflection current of 2 milli. Never mind, 2 milli is the current flows through the overall circuit. Okay, we want to convert the basic PMMC into a multi-range DC voltmeter with voltage ranges as here. So how to convert the basic, this is the general question. How to convert a basic ensemble movement or a basic PMMC into a voltmeter? How? Izzat, Imran.
Yes, yeah.
How to convert? Gelap pula. How to convert a basic ensemble movement or a basic PMMC into a DC voltmeter? How? Is that follow my lecture from the beginning, right? Is that?
Ya.
Apa jawapan dia?
Saya tak sure doktor.
Tadi buat apa? Tadi dengar tak?
Dengar.
Don't know. Have you downloaded chapter 2 notes? Okay. Duhair. Are you with me, Duhair? Duhair? But you can type, Duhair. You can type. How to convert basic PMMC or the unsolvable movement into a multi-range, into a DC voltmeter? How? Ramona, Shakira. How?
Yeah.
How to convert?
Connecting a number of resistors in series.
Pandai. By connecting, okay, for single range DC voltmeter, by connecting a multiplier resistance or a series resistance in series with the PMMC, right? So for multi-range DC voltmeter, we connect a series of multiplier resistance to the PMMC. That's why the sentence to convert a basic blah 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 into a, so we have to calculate RS. Okay, if you look at this question, it did not mention the term of RS. Okay, but how to convert? By adding multiplier resistance. Okay, so if you look at, so this is the basic picture of multi-range DC voltmeter. We have R1, R2, R3, and R4 connected to the PMMC. So now the range is 0 to 10, 50, 100, and 250 volt. So this voltmeter has how many ranges? Ramana?
4.
4. Okay, so we start with R4. This is the lowest R, okay? So R4 is equal to, okay, if we go to the basic calculation of DC voltmeter, RS is equal to S V range minus RM. Okay, so R4 or RS4 is equal to S V range minus RM. And we know that S is equal to 1 over I. 1 over 2 milli. We get 500 ohm per volt. Okay. Okay, actually, this is the general formula. No need to put R4 here. Okay, so at V4 range, now we tap the pointer at V4. Okay, we want to find the RS4 or R4 here. At V4 range here, we have only R4 and RM. This is disconnected from the circuit. Okay. So, okay, in this circuit, this is the general circuit. The pointer can be tapped into V1, V2, V3, and V4. This is the example only. The pointer is tapped at V2. Okay. So we refer to the above figure. R4 or RS4 is equal to S multiplied with V range minus RM. S is equal to 500 as we calculated. V range is 10 volts. This is the lowest range. At the lowest range, minus RM is equal to 50. We get 4.95 kilo ohm. Okay, now we go to the next range. We tap the pointer at V3. Okay, now the figure becomes this. We have RS3 and RS4. Okay, so at V3 range, we want to find RS3. We have calculated for R4. Okay, so please imagine this is we only apply R equivalent in this equation. Okay, R3 is equal to, this is our total actually, S multiplied with V range. Our total minus, we have RM here 50 and we have R4. R4 is 4.95 K. So now S multiplied with V range here become 500 multiplied with 50 because we tap at V3. V3 is 50 volts. We get 20K. So RS3 here is 20K. The same step for V2. When we tap the pointer at V2 range, we have R2. Okay. When we tap at V2, we have R2, 3, and 4. Okay, so R2 is equal to R total minus R3, R4, and RM. R total is S multiplied with V. S is equal to 500. V range now is equal to 100 volts. The third range. Minus 50 minus 20K minus 4.95K, we get 25K. Okay, the R become larger and larger. Okay, from 4.95K, 20K, 25K, and then this is the last range at V1 is equal to 250. Okay, 250 minus RM and then all R2, 3, 4. Which one? 2, 3, and 4. Okay. We have finally R1 is equal to 75K. Any question? Can I understand?
Can.
Okay.
Okay, so we go to tutorial of multi-range voltmeter. Yeah. Okay, this is number 6 in tutorial 2, a PMMC instrument. Okay, this with a FSD of 50 microamp. And okay, so 50 microamp is the current flows through this circuit. This is series circuit actually, series circuit. And RM is 1700. RM is here to be employed as a voltmeter. So PMMC instrument will be converted into voltmeter by what?
Putting in series.
Yes, by adding series resistance or multiplier resistance or RS to the circuit. Okay, so we want to design a voltmeter with 3 ranges, 10 volt, 50 volt, and 100 volt. Calculate the required values of multiplier resistors for the circuit of figure 5A and 5B. So in 5A, the RS, the series resistance are connected like this. In 5B, the series resistance are connected like this. Okay, there is a difference. Okay, now we do for figure 5A first. Okay, so this is the information given in the question. We have current equal to 50 micro, RM 1700, V range. We have 3 ranges. Calculate the required RS. Okay, this is the first figure. So how to find RS? We know that the basic formula is S V range minus RM. Okay, and we have to find S first. S is equal to 1 over I equal to 1 over 50 micro equal to 20 k ohm per volt. Okay. So now we start with, we can start at any point, okay? Because if we at any point, we have only one RS, okay? If we tap at 10 volt, so we only have R1 and Rm. If we tap at 50 volt, we only have R2 and Rm. Okay, because other R will be disconnected. At 10 volt range, RS1 or R1 is equal to SV range minus Rm. S is equal to 20K as we calculated before. Multiply with the voltage range is 10 minus Rm is 1.7K. We get 198.K ohm. So here R1 or RS1. Same procedure for 50 volt range. Okay, we just change the range to 50. We get the answer. The same step for 100 volt range. We just change the V range here. Any question? Any question? Okay, this is the next figure, figure B. Okay, we start with the lowest range. Okay, because at 10 volt, we have R1 and Rm. At 50 volt, we have R2, R1, Rm. At 100 volt, we have 3, 2, 1, and Rm. Okay, so we have calculated S. So we just proceed to RS1 or R1 here is equal to 20K multiplied with 10 minus 1.7K. We get this. Okay, at RS2 or at 50 volt range, 20K multiplied with 50 because 50 volt minus we have Rm and R1. Okay, minus and minus, we get 800K. So R2 or RS2 is 800K. Same goes at 100 volt range. We have 3, 2, 1 and Rm. So we want to find S3 or R3. It is equal to the R total minus all R. R total is S multiplied with V range. We substitute V range is equal to 100 volts and we subtract all R. Any question? Can you understand?
So far, so good, Doctor.
Open. Okay. Okay, now we go to the next subtopic. It is DC meter effect. Okay, so for voltmeter, we have voltmeter loading effect. We also have ammeter effect. we call it as ammeter insertion effect or loading of effect of ammeter. Okay, whatever. When a voltmeter is used to measure the voltage across a circuit component or across R, let's say R, the voltmeter is connected in parallel with the component because we want to measure voltage. If the resistance of voltmeter is not as high as compared to resistance of the circuit across which is connected, the measured voltage will be less than the actual. Okay, this called the loading effect because the voltmeter loads lower the effective resistance of the circuit and change the voltage reading. In voltmeter we have resistance, internal resistance. We have RS, right? Okay, and we have RM as well. So when we put the voltmeter across a resistor that we want to measure, we would get lower voltage as compared to theory, as compared to calculation. This we call as voltmeter loading effect. Why the voltage measured is reduced? Because in the voltmeter itself, it has internal resistance due to RS and due to RM. Okay, the voltmeter loading can be reduced by using a high sensitivity voltmeter. Okay, this is the so this phenomena is can be referred to Ohm's law, V equal to IR. Okay, when a voltmeter is connected to when a voltmeter is used to measure a resistor, we put the voltmeter parallel to the resistor. Okay, so the R in the voltmeter become parallel to the R that we want to measure. So the equivalent R becomes lower, right? Okay, let's say, but this is not a practical. Let's say the R that we want to measure is 10 ohm. The internal R in the voltmeter is 10 ohm also. So what is the equivalent R now? What is the equivalent R? Daniel? Daniel?
Ya, saya doktor.
Answer? Faster.
Tak sure doktor.
Okay. Boleh imagine tak? Okay. This is a resistor. We want to measure this resistor. We want to measure the voltage of this resistor. Okay, now how to measure the voltage at this resistor? We take a voltmeter, okay, and we tap at the resistor in parallel, right? Betul tak?
Betul.
Okay,
Ya.
so in this voltmeter, it has internal R due to RS and RM, right? Okay, so now let's say the R that we want to measure is 10 ohm. The internal R in this voltmeter is 10 ohm also. So now, what is the equivalent R of this connection? 10 ohm and 10 ohm.
5.
5. It will be half. Okay, if the two resistor has the same value, 10 and 10, connected in parallel, the equivalent R will be half. Okay, so now R equivalent will be lower, right, from the actual. The actual is 10. When we put the ohmmeter, when we put the voltmeter, that has internal R, the equivalent R become lower, right? Can. So if the R low, V will be lower as well. Understand or not? Understand or not?
This one, yes.
Okay, that's why we get lower voltage. Okay, due to the internal resistance in the voltmeter. When now R become R equivalent. When we connect a voltmeter at the resistor that we want to measure, R become R equivalent. R equivalent is less than the actual R, that 10 ohm. So if R lower, V will be lower as well. This is Ohm's law. When voltmeter is used to measure voltage across the circuit component, the voltmeter circuit itself is in parallel with the circuit component. The parallel combination of two resistors will reduce the total equivalent resistance. Therefore, the voltage across the component is less whenever the voltmeter is connected. This effect is called the loading effect of an voltmeter. Okay? That we want to learn in this subtopic, voltmeter loading effect. So consider this figure. We have 5 mega and 10 mega connected in series. So actually, V of R2 can be measured or can be calculated as this. What principle is this?
Voltage divider principle.
Yes, voltage divider principle, voltage divider rule. Okay, we put 10 mega, the resistor itself, divided with the series resistance in this path, multiply with the voltage supply to this path. It is same as the voltage source, 10 volt. So VR2 is equal to 6.66 volt. Now we take a voltmeter. This is voltmeter. We want to measure. So now this is from the calculation or from the theory. Now this one is from the measurement. We take a voltmeter to measure VR2. We know that in a voltmeter, there is internal resistance. Okay, let's say the internal resistance is 10 mega, the same as 10 mega here. So, 10 mega parallel with 10 mega, we get 5 mega. So 5 mega here, then you R equivalent will be 5 mega here. 5 mega divided with 5 mega plus 5 mega here plus 5 mega here. Okay, multiply with 10, we get 5 volt. So now with the voltmeter, okay, tap to the resistor, the voltage become less from the actual. This is actual or from the theory or from the calculation. It is from the measurement, we get lower V. Okay. Figure shows a simple series circuit of R1 and R2 connected to a 100 volt DC source. If the voltage across R2 is to be measured by voltmeter, okay, this is voltmeter. Okay, class, this is series or parallel circuit?
Series.
Series circuit. Do not be confused with this voltmeter. This is not connection of the circuit. Okay, this is only voltmeter that tap to the R2 because this voltmeter want to measure VR2. Okay, so actually this is series circuit. This is not the connection of the circuit. We just put the voltmeter parallel to R2 because we want to measure VR2. If the voltage across R2 is to be measured by voltmeter having sensitivity of 1000 ohm and a sensitivity of 20,000 ohm per volts. Okay. Find which voltmeter will read the accurate value of voltage across R2. Both meters are used on the 50 volt range. Okay, we have two voltmeter. both voltmeter have 50 volt range, but the first voltmeter has sensitivity of 1 k ohm per volt. The second voltmeter has sensitivity of 20 k ohm per volt. Which one of the voltmeter will read the accurate value of VR2? Okay, actually the higher sensitivity, the higher accuracy. Okay, now let's find VR2 by using calculation or manual or theory without voltmeter. Okay, without voltmeter. This is from the calculation, from theory. True value of VR2. Okay, by using voltage divider principle, 10K multiplied with the voltage source 100 volt divided with the all are connected in series with R2. It is 10K plus 10K. We have 50 volts. Okay, now we want to use voltmeter with the first voltmeter with sensitivity 1 kilo ohm per volt. Okay. Sensitivity is 1 k ohm per volt. Imagine that here now is the first voltmeter with sensitivity 1 k ohm per volt. We want to know what is the R in the meter. So R total, we know that R total is equal to S multiplied with V range. Okay. We know that voltage range of the voltmeter is 50. So R is equal to S multiplied with V range. S is equal to 1K multiplied with 50, we get R. The R total of the voltmeter, of the first voltmeter. Okay. It includes RS and RM. So now the new R equivalent here becomes what? The new R equivalent becomes the new R equivalent here becomes, siapa yang mencari mangsa? Nak cari mangsa ni. Bawah-bawah sikit lah pula. Akil Ahnaf.
Ya, ada.
Suka. Akil Ahnaf suka sebenarnya. Okay, now what is the new R equivalent here?
Saya suka sebab saya tak tahu tu.
Kira. You have calculator? Calculate it now.
Ha?
Calculate it now. Calculate. What is the new R equivalent here now? When we put the first voltmeter at R2 to measure VR2, what is the new R equivalent? Before we...
Meter tu berapa tu? 50
Apa? Ha?
50 dekat voltmeter tu 50 K
Apa? 50K? You pay attention tak tadi?
Tak faham sangat.
Tak faham tak tanya?
Malu tu.
Malu. Malu bertanya sesat.
Jalan.
MT, what is the new R equivalent now? MT. Mana MT? MT, are you with me? MT? Tidur ke apa? Winston, what is the new R equivalent now? Winston?
Hello?
What is the new R equivalent now?
Tak tahu, doktor.
Tak tahu lah. Faham tidak? Finster faham tak?
Tak faham doktor. Tak faham.
Tak faham? Apa tak tanya? Mentang-mentang online tak nak tanya. Tuan Shalin. Shalin?
Saya doktor.
What is the new R equivalent now? When we connect the first voltmeter with sensitivity of 1K, we get our total of the meter is 50K. We tap to R2. What is the new R equivalent now? You tell me how to calculate. No need to 8.33. Ikhwan, how you get this?
Yang R2 kan dengan meter tu kan parallel kan. So 1/50 kilo tu tambah dengan 1/10 kilo. Lepas tu dapat.
Dapat
Dapat.
Dapat terus?
Bukan kan?
Kena lah 1/10.
kilo ohm.
Finally, you have to 1/, the answer, right?
1/.
Okay. In other words, the R equivalent now is 10K parallel to what?
50K.
50K. The answer is here. 10K parallel with 50K. And you get 8.33K ohm. Is it right?
Yes.
Akilah now. Okay. So now the new R equivalent here is 8.33K. So how to find VR2 from the voltmeter? A is 10K, 8.33K here. Okay, after we calculate this, 8.33K divided with 10K. Okay, plus 8.33K ohm. Multiply with the voltage source 100 volts. We get 45.45 volt. Okay, now we observe that by using voltmeter, we get less voltage as compared to the theory. This is from the calculation. It is by using voltmeter, we get lower value. Because of what? Because of what?
Loading effect.
Voltmeter loading effect. Azin kan?
Yes, saya.
Okay, so now we go to the next voltmeter with sensitivity of 20K ohm per volt. Okay, the same step repeated. We calculate for R in voltmeter. Okay, 20K is the sensitivity, right? Yes, sensitivity multiply with the V range, the same voltage range of the voltmeter, 50 volts. Okay, in your calculation, do not include the unit. Okay, do not include ohm, V, and V here. Okay, just put the kilo, milli, and so on. So we get 1 mega ohm. Okay, 1 mega ohm. And how about the new R equivalent? Okay, so 10K parallel with 1 mega. We get 9.9K volts. Okay, now what is the next step? Now we get the R equivalent. The next step is Badrul Amin. Tak nak lah, dah sebut hari tu. Kamarina. Kamar ni bulan kami. Kamarina. Are you with me?
Kamarina ada 2 doktor.
Lah. Kamarina mat apa ni? Mak Razi. Boleh lah. Sekejap lagi tanya Kamarina satu lagi. Kamarina, Mak Razi. Okay. The next step is okay, nampak tak ni? Dot. Please continue. After we get our equivalent of the second voltmeter, the next step is Kamarina ada tak ni? Kamarina Mak Razi tak ada
Ada doktor.
Ada tak?
Ada doktor.
You
Saya.
Okay, the next step is Kamarina section 3 itulah saya tak pernah dengar nama. Last semester I ajar section 2. Okay, the next step is to
Saya tak tahu.
dari tadi.
Ya.
You follow my lecture from the beginning or not?
Ya.
Habis tu? Understand or not?
Ya doktor.
Understand or not? Kamarina satu lagi lah. Ahmad. Apa ni? Satu lagi. Kamarina want try to answer? Kamarina Mak Razi?
Saya tak tahu.
Okay, the next Kamarina. Ahmad Syukri. Okay, what is the next step? After we calculate R equivalent for the second multimeter, second voltmeter, the next step is Kamarina. What is the next step? Tak faham ke? Okay, who want to answer? What is the next step?
Cari voltage.
Voltage apa? The voltage VR2, right? Okay, so now please no need to calculate. Let me know what is the value here. Come on. How to find VR2? How?
1000 K parallel dengan 10K divide by 10K.
Okay, actually we have calculated. It is 9.9K. Okay, now so how to find VR2?
9.9K divide by 10K plus 9.9K times 100 volt.
Yeay, Ramona. Cepat, tepuk tangan. Bagus. Okay, so and then the answer is? The answer is?
49.75 volt.
Okay, is it right, Philip? 49.
49 and check. Looks like it is.
Is it right?
Looks like it is, unless I have to double check this.
Apa Philip cakap apa?
It's good.
Is it right?
Yeah, looks like it.
Philip calculating.
Yeah.
Okay, how about others? Is it right? 49 point something.
Yes, madam. Betul.
Okay, so which voltmeter read the more accurate result? Which voltmeter read more accurate?
Yang ada high
High
sensitivity.
sensitivity.
Okay, voltmeter 1 or 2?
2.
A or B?
LB2.
Okay, number 2, right? The second, because of higher sensitivity and the voltage measured closer to the actual. What else? Okay. Okay, the other example, 2 different voltmeters are used to measure the voltage across RB in the circuit. The meters are as follows. As meter 1, S is equal to 1K, meter 2, S is equal to 20K, RM, this, RM, and then the same range, 10 volt, 10 volt. Calculate voltage across RB without any meter across it. Voltage across RB when meter 1 is used. Voltage across RB when meter 2 is used. Error in the voltmeters. Okay. The first is to find RB without any meter, meaning that from the calculation, okay, or the actual or from the theory. This is by using voltage divider principle. 5K plus 25K plus 5K, multiply with the voltage source 30 volt, we get 5 volt. Okay. Now we use the first voltmeter, meter 1. Okay. So we want to know what is the R of the voltmeter. How to find R? We have the sensitivity. R total is equal to S multiply with V range, S is equal to 1K multiply with 10, we get 10K ohm. Okay, now 10K will be parallel with 5K here because this voltmeter connected in parallel to measure VRB. The new R equivalent will be 3.333K. Okay, it is lower than the actual RB 5K ohm. So VRB is equal to 3.33K ohm multiplied with the voltage source 30 divided with summation of R in this part 25K plus 5K, we get 3.526 volt. Okay, this value is lower than the actual value. The next voltmeter with sensitivity of 20K. Okay, now we ignore RM because the calculated R total, let's say 200K is including RM and RS. Okay, R total of voltmeter 2 is equal to S V range. S is equal to 20K multiplied with the V range is 10 volts. We get 200 kilo ohms. So the new R equivalent here will be 200K parallel with 5K. We get this 4.878K. We find that this value is lower than RB because of voltmeter loading effect. Now VRB is equal to, we take the new R equivalent, multiply with the voltage source divided with the summation of R in this path. We get 4.879 and this value also is lower than the actual V. The actual V is what? 5 volt, okay? So now we find the error. We know that to find error, we get the difference between the actual and the measurement divided with the actual, multiply with 100. So for voltmeter A or voltmeter 1, the error is 29.47%. For voltmeter 2, this should be 2, okay? Take the difference between the actual and the measurement divided with the actual, multiply with 100. We get 2.06%. We found that the error for voltmeter number 2 is lower than the voltmeter number 1, and we due to the higher sensitivity of meter 2. Understand or not? Understand or not?
Yes.
Okay. Ini dah. Okay, this is number 7. I think don't need to discuss, okay, because it is same as your lecture note. We have voltage range of voltmeter connected to measure R2. Okay, R2 is 50 kilo ohm. R1 is given as well. R1 is 70 kilo ohm. Calculate V2, VR2 without meter connected with a voltmeter having sensitivity of 20K, voltmeter sensitivity of 200K. So the first is we find VR2 by calculation from theory. It is the actual without meter connected, and we get VR2 is equal to 5 volts. Okay, this one is when we use sensitivity of 20K, we have to find the R total of the meter. Okay, S multiply with the V range. The V range is 5 volts. Okay, we get the R total, and then we find the R equivalent at here. Okay, we get 33.3 kilo ohm, and then we can find the VR2 by using that voltmeter, and we get lower value of volt as compared to the calculation. As compared to the theory, we have 5 volt. Okay. And then how about sensitivity of 200 kilovolt? You calculate. Okay, the answer is 4.86 volt. Okay, any question? Can understand? Same as slide. I think no need to discuss, right? Okay.
Doktor. Nanti doktor update kan tutor ni?
Nanti. Later ya.
Okay.
Okay. Nak tanya lah. Best juga tanya ni. Because during face-to-face class, I like to ask my student. Tan Kah Ling. Okay. For voltmeter with sensitivity 200 kilovolt, kilo ohm per volt, what is the R total of the voltmeter?
Sorry, doctor, I haven't count. I haven't do this tutorial.
Sorry?
I have no answer for this.
Why?
I haven't calculate. Don't know how to calculate.
Don't know how to calculate. This is very you can calculate without calculator as well. Very basic calculation.
7C.
Huh?
Is it 7C? Is it 7C?
Sorry?
7C ada question.
Saya tak faham lah. Dan Kahlin cakap apa?
7C.
Ha?
7C. Dia tanya 7C ke?
Apa tu? 7C, yes, 7C, yes. Voltmeter with sensitivity of 200K ohm per volt. So, what is the next step? What is the first step?
What is first step?
You are calculating?
Yeah.
Hmm.
It might take me some time.
Siti Maisarah, what is the first step?
Doktor, race dia sama je ke?
Tak je nak test. Siti Maisarah? Are you with me?
Ya.
What is the first step?
Cari R.
R. So, how to find R?
S darab dengan range.
Okay, what is the value of S? What is the value of S?
The S is
200
200 what?
kilo ohm.
Per volt. 200k.
Oh, okay.
Tadi siapa nak tanya tadi? Tan Kahling.
Yeah, madam. Just follow the in B, then replace for the first step, replace the 20 kilo ohms with 200, then we get 1000 kilo ohm, then continue calculate with the equivalence resistance with parallel since the circuits are the same. So also the RE2 is the same, 33.3 kilo ohm.
RE2 is 33.3 kilo ohm. Are you sure? Sarih.
No.
What is the RE? R equivalent, then the R equivalent. How to calculate? Everyone please calculate. And make sure you get 4.86 volt. Get the answer? 4.86. What is the value of 47? Is it RE? R equivalent?
Yes.
Okay, class. If you get the final answer 4.86 volt, please type here. Yes. Type yes. Get the answer, type yes. Okay, good, Winston. What about others? Almost there.
Doktor.
Good.
Doktor.
Ya?
Yang tu 1 mega parallel dengan 50k kan?
Yelah tu kot. Berapa 200k multiply with 5. 1 mega. 1 mega. 1 mega parallel with berapa? 50 50k.
50k.
Okay. Good. Hasif, Syawal, Hani, Hafiz Fikri, Faris Akmal, Bona, Philip, Al-Amin, Winston, Arif, Afifi, Akmal Luqman, got. Okay, good. Good. Atira, Ahmad Izzat. Ikhwan. Duhai. Okay, good. Okay, this is the last subtopic. Okay, the last subtopic. Last tapi macam banyak. Okay. Ammeter insertion effect. Actually, this is the effect of ammeter. Same for loading voltmeter loading effects. So this is ammeter loading effect. Okay, but in our note, this the term is ammeter insertion effect, the same. Okay, but we know that if you want to measure voltage, we put the voltmeter parallel to the component, right? Parallel to the resistor. If you want to measure current through the circuit, we put the ammeter in series with the circuit. Inserting ammeter in a circuit always increase the resistance of the circuit. Okay. For voltmeter, loading a voltmeter will reduce the voltage because of what? Ohm's law. Okay, so inserting ammeter will reduce the resistance of the circuit and thus always reduce the current because V is equal to IR. When I is equal to V over R. The R must be higher, okay, not reduced. Okay, yes, increase R and reduce current. Okay, the expected current without ammeter is, okay, I is equal to V over R. But by placing the meter, the ammeter, we will put the ammeter in series with the circuit. So the internal resistance in the ammeter will be series with, let's say, R1. So the new I is equal to V over R1 plus Rm. Rm is the internal resistance of the meter. R1 is the R in the circuit that we want to measure. Okay, so this is an example. We want to measure the current flows through this path. Flow through R1. We put ammeter in series with R1 like this. Okay, so in theory, I1, okay, this is without ammeter. I1 is equal to, how we get this? 666.666 milli. How we get this? Ignore this ammeter. We have a parallel circuit with R1 and R2. R1 is equal to 3 ohm. R2 is equal to 1.5 ohm. The voltage source is 2 volt. How to find I1 and I2? I2 is equal to 1.
Current divider.
V over
Current
R.
potential divider.
Wow. Okay. How to find I2? What value divide or multiply with what value? How to find I2?
1.5
Okay.
divide with 1.5 times 3 times 2 volt.
What principle of that? What principle? Siapa jawab tadi? Zahiri? What principle?
Current divider.
Current divider. How to find I2 by using current divider?
3 divided by 3 plus 1.5 times I total.
I total. So we have to find the I total first, right? Okay, other method?
V over R2.
Yeah, that's right. Ramona, V over R2. So, what divide what?
2 divided by 1.5.
We directly get the answer because this is parallel circuit. 2 voltage from the source will give 2 voltage here and 2 voltage here. parallel circuit. Okay. So 2 divided with 1.5, we get 1.233. And then how about the current across, the current flows through R1?
2 divided by 3.
Okay, so 2 divided with 3, we get 66.66 milliamps. Okay, now we put ammeter at this path to measure current flows through R1. Okay, but this ammeter has internal resistance. Okay, let's say in this example, the internal resistance is 0.5. So since this is series connection, we have to add with 3. Okay, so we get the new I 571. Okay, it is lower than 666 milli. How to get 571 milli? How?
2 divided by 3 plus 0.5.
Yes, okay. 2 divide with, in the bracket, 3 plus 0.5, we get the new current. Okay, so with ammeter connected to the circuit, okay, because of the measurement, the current, we might get lower current. Okay, 571 is lower than 666 because of current internal resistance of the ammeter. Okay, this is how to calculate the error. Okay, so this is an example. A current meter that has an internal resistance of 78 ohm. Okay, current. Ammeter with internal resistance of 78 ohm is used to measure the current through a resistor RC here in figure. Determine the percentage of error of the reading due to ammeter insertion effect. Voltage source is 50 volt. This is without meter. This is when we put ammeter to this path. Okay. Percentage error. Percentage error. So to find the percentage error, we should know the measurement. Okay. The value of measurement. Okay, we should find the actual current flows through RC. How? By using current divider principle. Okay, because we have RA here. So voltage source 50 volt cannot give directly 50 volt at 1K here and RB and RC because of 1K at RA. Okay, so we have to find the total current. We have to find the total resistance first. 1K parallel with 1K, we get 0.5K, and then plus with 1K, we get 1.5K. This is the total resistance of this circuit. And then we find the total I. I is equal to V over R, 50 divided with 1.5K, we get this. This is the total current. Okay, so how to find the IRC? We put the R, the neighboring R. Okay, it is 1K, the same. 1K multiplied with the current source, it is 33.323 milli divided with summation of resistors that is connected in parallel. So just 1K plus 1K. Do not add this 1K, okay? Okay, and then we get 16.66 milliamp. This is the actual IRC. Okay, now we put the ammeter, and the ammeter has internal resistance of 78 ohm. We have to consider this in our calculation. So now we want to find the total R, the new R total. Okay, so 1K plus 78 is 1078. Will be parallel with 1K, and then this one plus with 1K here, we get this. Okay. Now we repeat the same step. We want to find the total current. Okay, the new current. Okay, V divided with R. 50 divided with the new R, and we get the new I total. Okay, now we want to find the IRC. Okay, we put the neighboring R, it is 1K, 1K multiply with the new current source, 32 milli, divided with the summation of R that is connected in parallel. It is 1K plus 1K plus 78. Do not need to add this RA. Okay, and we get this. Now we can calculate percentage of error by get the difference between the actual and the measurement. 16 minus 15 divided with the actual, multiply with 100. The error is 4.95%. Any question? Any question?
No.
Please ask me rather than asking your friend during exam. Please ask me during our lecture rather than asking your friend during test and final exam. Any question? Don't be shy. Any question? No.
No.
Okay, this is the next example. Simpler than the previous actually. Okay. Actually, this example should be located before the previous. Figure shows a simple series circle of RA and RB connected to a 100 VDC. If the current flows through RB is measured by an ammeter having RM is equal to 50 ohm, calculate the insertion error of the meter. Actually, I have edited this figure. Never mind, I will re-upload in Microsoft Teams. Okay, this is the actual figure when we put the ammeter. If the current flows through RB, actually only one current flows in this path. IRB is equal to IRA is equal to I total. So we can put ammeter anywhere in this path. Calculate the insertion error of the meter. So we want to calculate the actual first. I is equal to V over R 100 divided with the summation of R. We have 5K plus 5K. So this is the actual current. Now we want to calculate current because of ammeter insertion effect. 100 divided with the summation of R. We have 5K, 5K, and don't forget we have 50 ohm in the ammeter. So this is the new R. Now the error is the difference between actual and measurement divided with the actual multiply with 100, we get 0.5% error. Any question? Okay, before we start our class, I'm writing tutorial to number 8, but I did not finish the solution. I think I leave it to you. You can solve it by yourself. Number 8 is quite challenging, but you can try it. It is good to try. Okay, I will upload this. I don't want to finish number 8. Leave it to you. You can read this question and you can solve. Okay, this subtopic of ammeter insertion effect, in tutorial 2, it is number 4. Okay, number 4. Number 4 is ammeter insertion effect, but this question is very simple. I think no need to discuss. Okay, because just as our lecture. Okay, that's all for today. Next week we will learn the other subtopic. I think this is the last subtopic of chapter 2, ohmmeter. Okay, quite long. Okay. Huh?
I'm done here. I ask this slide PPT will be uploaded again, right?
Yes, I will re-upload because I have edited here and there.
Because I think I ordered before, so my version is different from Dr. One. So thank you, Doctor.
I do not understand.
I mean the version that I get is only 50 slides, something like that. Maybe I altered it before, so that's why my slide is quite a bit different with Dr. One. So I hope Dr. they upload again.
Dr. One?
Yeah, with yours one.
Who is Dr. One?
No. I mean the slide I get from the MT is different from what lecture showing in the MT right now. So I wish the doctor can re-upload again the latest slide.
Yes.
I got the wrong one maybe. Thank you, doctor.
Okay. Any question from others?
No.
No.
Am I too fast?
A little bit.
Huh? Little bit
Okay.
Laju sikit tapi ada rekod ni
Boleh
okey lah.
lah.
Okay.
Kinda fast.
Ada rekod boleh tengok balik.
Kan? Anik, okay now I stop recording.